Welcome to the presentation of the paper Security of Public Key Encryption Against Resetting Attacks. My name is Patrick Struck and this is joint work with Juliane Kraemer. In this work we're looking into public key encryption. So we have two communicating parties, Alice and Bob. When Alice wants to send over some message to Bob, she will use Bob's public key to encrypt the message using the encryption algorithm and then send over the ciphertext to Bob. And then Bob used the corresponding secret key to decrypt the ciphertext and then get the message of Alice. Then in between we have the adversary who will see the ciphertext that Alice sends over to Bob. And we deem such a scheme secure if the adversary does not learn anything about the underlying message M from the ciphertext C. A standard security notion for public key encryption scheme is indistinguishability under chosen plaintext attack. In this security notion, the adversary gets the public key as an input, and then it gets oracle access to a challenge oracle, which also gets the public key and some secret bit B as input. The adversary can then invoke this oracle on two messages, a left and a right message. The oracle will, depending on this bit B, pick either the left or the right message, encrypt it to get the ciphertext, and then send the ciphertext back to the adversary. And after many queries, the adversary then is supposed to output a bit B prime as its guess for the bit B, and the adversary then wins if it guesses the bit B correctly. Now in this notion, the randomness here is implicit in the encryption algorithm when the challenge oracle encrypts the message. If we rewrite this to explicit randomness, we have the same setting with the adversary and the oracle. Now if the adversary sends two messages, the oracle will first generate the random coins Ri for the ith query of the adversary, and then deterministically produce the ciphertext by encrypting either the left or the right message using this generated random coins, and then send back the ciphertext to the adversary. Now, a crucial part for this notion is that these random coins are generated independently for every query of the adversary. And main question is, what happens if this is actually not the case? There are different flavors of what can go wrong with the randomness used during encryption. In this work, we are considering the scenario mentioned by Garfinkel and Rosenblum, as well as considered by Ristenpart and Jilek. So they have the setting where the randomness is obtained from the current state of a system. And if we use virtual machines, then they can create a snapshot of such a security critical state from which the randomness is then derived. And this entails that if such a snapshot is then restored, then this would result in a reusing of the randomness. This gave rise to the resetting attack model proposed by Jilek in 2010, which is a strengthening of the INT-CPA security notion seen on the last slide. So here we have the adversary, and it gets some target public key PK star as an input. The adversary has then access to some challenge oracle, which also receives the target public key, a challenge bit B, and some random coins R star as an input. The adversary can invoke this oracle on two messages, and the oracle will pick, depending on the bit B, either the left or the right message of the adversary and encrypt it under this target public key and these random coins R star, and then send back the ciphertext to the adversary. In addition, the adversary gets another learning oracle, which receives also this random coins R star as an input. This oracle can be invoked by the adversary on some public key and a message. The oracle will encrypt the message under the public key queried by the adversary using the random coins that it receives as an input, and then send the ciphertext back to the adversary. In the end, again, the adversary outputs a guess B prime for this challenge bit B and wins the game if it guesses the bit correctly. Now there are some queries which are forbidden in this security notion because this would result in trivial wins for the adversary. So for instance, the adversary is not allowed to make two queries to the challenge oracle which agree in one of the messages but differ in the other. So for instance, if the adversary queries the message M0 and M1, it can then not later query the same message M0 together with a different message M2 to the challenge oracle. And the reason is quite simple, because clearly if the bit B is 0, then it will see the same ciphertext twice, while in the other case, since there were two different messages M1 and M2, it will see different ciphertext. Furthermore, the adversary is not allowed to query message together with the target public key to its learning oracle if this message is also queried to the challenge oracle. As a separation between the INCPA security notion and the resetting attacks, Juliane considers the hybrid encryption scheme, and concretely the instantiation of the hybrid encryption scheme using the one-time pad as the underlying symmetric key encryption scheme. So it will generate a key for the one-time pad encryption, which it will encrypt using the underlying public key encryption scheme, and then use the one-time pad to encrypt the actual message. Now, due to the fixed randomness in the resetting attack setting, this means that the same one-time pad key is used for every encryption. And for this, the adversary with one learning query to its learning oracle on an arbitrary message, the adversary can learn this one-time pad key, which will be used every time, and then use this key for decrypting the ciphertext part C2 of the challenge ciphertext. In this work, we extend this separation result by showing that not just this particular instantiation of the hybrid encryption scheme is insecure against resetting attacks, but in fact every instantiation is insecure. And for this, we give the following attack. So with an adversary picks two messages, M0 and M1 at random, and invokes its challenge oracle on this message to get the ciphertext consisting of the two ciphertext components C1 and C2. It will then query the same two messages to its learning oracle on a different public key than the target public key. This is why this query is allowed, because it's not the target public key. And for these two queries, the adversary gets back the two ciphertext here. And it then can simply check for the second part of the ciphertext, so which of the two ciphertext it gets back from the learning queries, for which the second part equals the second part of its challenge ciphertext. And due to the deterministic encryption using the underlying symmetric encryption scheme, this will be equal for one of the two messages. And this then enables the adversary to perfectly distinguish the cases, whether the left or the right message was encrypted. We show that furthermore that some other schemes are insecure against resetting attacks, and this includes the canonical LWE-based encryption scheme due to RegEff, and the code-based encryption schemes HQC, RQC, and Rollo2, which were submitted to the NIST post-quantum cryptography standardization process. Along with the security notion against resetting attacks, Juliane also proposed the simplified security notion, where the adversary is restricted to only one challenge query to its challenge oracle. This is a standard simplification for these INCPA-like security notions. And the claim made is that security in this simple setting of a single challenge query implies security against an adversary making multiple queries to the challenge oracle, even for resetting attacks. And the given proof for this is via a standard hybrid argument. So this is the setting for the proof. So we have an adversary, and in fact it tries to distinguish whether its challenge oracle is instantiated with the bit being 0 here on the left side and the bit being 1 here on the right side. Now Juliane proposed the following hybrid games GI, where in the game GI the first I queries are answered by encrypting the right message that the adversary queried, while the last Q-I queries are encrypted using the left message that the adversary queries. This means that the game G0, for this always the left message is encrypted, so this corresponds to the case of the oracle being instantiated with the bit b being 0, while GQ, all the message, for every query the right message is encrypted, which means this game corresponds to the oracle being instantiated with the 1, while all the other games are in between. And then Juliane proposed to you to do a hybrid argument over these games. So more technically, if we have an adversary that can distinguish two consecutive hybrids, the games GI minus 1 and GI, then we can construct an adversary which makes only a single challenge query against the resetting attack game. Now we have an adversary which makes here Q queries, always consisting of two messages. Now for the first I minus 1 queries, both games will respond by encrypting the right message that the adversary has queried. For the ith query, the game GI will return the ciphertext obtained by encrypting the left message that the adversary queried, while the game GI will return the ciphertext obtained by encrypting the right message of the adversary. And for all the remaining queries in both games, the left message that the adversary queried will be encrypted. So you can see the only difference in this game lies in the ith query, while all the other queries are answered the same. Now for the reduction, it will, except for the ith query, all the other queries will be answered by using the learning oracle from the resetting attack game. So for the first I minus 1 queries, the reduction will take the right message of the adversary and send it together with the target public key to its learning oracle and send the response back to the adversary. While for the last queries, it will pick the left message of the adversary together with the target public key and forwards it to the learning oracle as well as the response back to the adversary. And then for the ith query, the reduction will take the challenge will take the two messages of the adversary and forward it as its own challenge to its own challenge oracle. And then depending on whether its challenge oracle on the bit of its own challenge oracle, it will either simulate game GI minus 1 or game GI for the adversary. So if the adversary can distinguish, so can the reduction by only making a single query to its challenge oracle. However, this proof was identified as flawed by Patterson, Schult and Seaborn in 2014. And they observed that the reduction in fact makes a forbidden query. Now going into the problem of the proof. So let's consider the case that the adversary now for the ith query queries two messages m0 and m1 to its challenge oracle. For this query, this is the query that the reduction will forward, so it will also invoke its own challenge oracle on the message m0 and m1. Now if the adversary for the I plus 1th query queries the message m1 and m0, so it just flips the order of the two messages to its challenge oracle, then this means that the reduction will query the target public key together with the left message, which is now the message m1, to its learning oracle. However, this query is forbidden because now the adversary queries a message to its learning oracle together with a public key, which it also queried at some point to its challenge oracle. So this raises the question whether this implication of security against an adversary making a single challenge query implies security against an adversary making multiple challenge queries holds also for the resetting attacks. In our work, we then show that the issue lies not in the given reduction, but instead it lies in the hybrid games. For this, we consider two types of special queries. The first one are flipping queries, which are essentially the one for which Patterson et al. Pointed out that the reduction does not go through. The other one being repeating queries where, well, as the name suggests, the adversary just makes the same query twice. And both of these queries are allowed in the security notion. Now, if we consider the two hybrid games, GI minus 1 and GI, we can consider we can give an adversary that can distinguish the games almost perfectly by making these queries. Now here we consider the flipping queries. So we have an adversary, and for the ith query, it will query the messages m0 and m1, and for the following query it will make a flipping query M1 and M0. Now in game GI-1, for both of these queries, it will be encrypted by taking the left message of the adversary. So the ciphertext CI will be the encryption of the message M0, and the ciphertext CI+1 will be the encryption of the message M1. And this means that the ciphertext will most likely be different. However, in the game GI, the ciphertext CI will be obtained by encrypting the right message, while the ciphertext CI+1 will be obtained by encrypting the left message. And this means that for both these ciphertexts, the message M1 will be encrypted. And this means that the ciphertext CI and CI+1 will be equal in this game. This means that these flipping queries allow the adversary to distinguish the two consecutive hybrid games GI-1 and GI almost perfectly. And the same argument also applies for the repeating queries, with the only difference that then the ciphertext will be equal in game GI-1 and different in the game GI. So this means that the proof approach cannot be fixed by changing just the reduction and how the reduction responds to the queries of the adversary. To restore the claim that the single challenge security implies multiple challenge security, we then give an alternative proof for the claim. And mainly we change the existing proof in two different ways. So first, we use two hybrid arguments instead of just one hybrid argument, which is essentially the part which solves the problem of the flipping queries. And second, for each of the two hybrid arguments, we only do the hybrid argument over the number of non-repeating queries by the adversary, which we denote by Q star, which solves the problem of the repeating queries. So we have the picture from before, so we have the adversary, which tries to distinguish the oracles being instantiated with a bit B being 0 or with a bit B being 1. And now in this proof, we consider some intermediate oracle, which just responds by encrypting random messages for every query. We then give some hybrid games Li, which work as follows. For the first I queries, it will encrypt a randomly chosen message, while for the remaining Q star minus I queries, it will encrypt the left message of the adversary. And whenever there's a repeating query by the adversary, it will just output the same response as the first time this query was made. For these hybrid games, it holds that L0 corresponds to the challenge oracle being instantiated with the bit B being 0, while LQ star corresponds to this intermediate oracle which just returns the encryption of randomly chosen messages to the adversary. Similarly, we define games Ri, where the first I queries are answered by encrypting also a random message, and the remaining Q star minus I queries are answered by encrypting the right message of the adversary, and likewise repeating queries are just answered by repeating the response. And for this, it also holds that game R0 corresponds to the challenge oracle being instantiated with the secret bit B being 1, while RQ star corresponds to this intermediate oracle by just returning random messages. And in fact, the two games LQ star and RQ star are in fact equal. For this, we can then do the two hybrid arguments. So the first hybrid argument is which we do over the hybrid games Li, and the second hybrid argument over the hybrid games I. How does this look like for the games Li? So we have an adversary which makes these Q star non-repeating queries to its challenge oracle. And now for both games Li-1 and Li, the first I-1 queries will be answered by just picking a random message and encrypting this message under the random coins R star. For the ith query in game Li-1, the left message of the adversary will be encrypted, while for game Li, also a random message will be chosen, which then will be encrypted. And for all the remaining queries in both games, the left message gets encrypted. So again, we have that the only difference lies in the response of the ith query for the adversary. And we then still have that reduction now for every other query except the ith query, will respond with the learning oracle. So for the first I-1 queries, the reduction will simply pick a message at random and invoke its learning oracle on this message and send the response back to the adversary. And for the query I+1 up to the query Q star, it will simply pick the left message of the adversary, forward it to its own learning oracle, and send the response back to the adversary. And for the ith query, the reduction will forward the query of the adversary to its own challenge oracle as the response back to the adversary. Now the main difference is now for the ith query, where the adversary queries the message m0i and m1i, the reduction does not invoke its challenge oracle on the message m1i, because it invokes it on the message m0i and a randomly chosen message. This enables then the reduction to be later able to query the message m1i to its learning oracle if the adversary makes a flipping query. And a very similar argument applies to the other hybrid games Ri. Now if we look at the adversary, let's consider the case of this flipping query. So if the adversary, and for the ith query, it invokes the oracle on m0 and m1, and for the following query on the flipping query m1, m0. And for the first one, the reduction will then take the left message m0 together with a random message and invoke its own oracle, its own challenge oracle on these two messages. And now for the second one, it will pick the left message of the adversary, which is the message m1, together with the target public key, and forwards it to its learning oracle. But now this query is valid because the adversary never queried the message m1 to its challenge oracle. And with this, we can show that the security against a single challenge also implies security against multiple challenges, even for the resetting attacks. And in comparison to the claim made by Juliane in 2010, we only get an additional factor of 2, which stems from the fact that we use 2 hybrid arguments compared to 1 hybrid argument. To wrap up, in this work we studied the resetting attack model proposed by Juliane. And we showed that many schemes are susceptible to resetting attacks by showing that they are insecure with respect to the security notion. We then show that the single challenge security in fact implies multiple challenge security even for the resetting attacks. For this we showed that the original proof approach does not work, and then we give an alternative proof for the claim. This concludes my presentation. Thank you very much.